Welcome back, everybody. This is a follow-up to my video on flatness. I alluded to a concept called datum overlap, and I thought I'd put together a little example. It's a fairly contrived example in one of its more simple forms, but it should illustrate why you need to be aware of this concept when you're putting together the drawings of parts that go together in an assembly. So let's say someone's tasked with creating a go and a no-go gauge for inspecting this feature here. They go through and they do the math and find that the go gauge needs to be 10 millimeters and the no-go gauge needs to be 20 millimeters. So this is the gauge that they come up with. And they want to save money, so they give it a really big flatness tolerance on the Datum A, but they want a very tight overall tolerance, so they give it a profile of 0.02. And someone has the bright idea, well, we're getting one gauge block that's going to be really, really close to 10 millimeters tall. Why do we make a second no-go gauge block when we can just stack two go gauges on top of each other and get a block, an equivalent height of what should be really close to 20 millimeters? This idea that they had is actually pretty common in the inspection world. People ring together gauge blocks all the time, but in this case, it was a bit of a problem, and it'll become clear soon. So you can see the enormous variation in the Datum A surface, but the height came at pretty bang on at 10 millimeters. Assuming that there's no instructions on the gauge or that come with the gauge about how to stack them, you might end up with a few different permutations and orientations with the gauge blocks. The first one might look like something like this, where you've got the Datum A surface on the granite, and then the second part has the Datum A on the profile side of the first block, in which case there is no issues. The actual material envelope of the two parts, or the assembly, is 20 millimeters. Another scenario might look something like this, where you've got, again, Datum A on the granite, and then you have the two profiles facing each other. And in this case, once again, the actual mating envelope of the two parts together of the assembly is 20 millimeters. We haven't gone over all the different ways these things could be stacked, but here's the sort of the interesting one and the name of the video. This is the two Datum A surfaces with their extreme surface variations facing each other, and because those surface variations happen to be complementary, when you measure the actual material or the actual mating envelope of the two parts, you actually get 19 millimeters. So what's going on here? Well, this is one of the oddities that arises when you take measurements from an individual part and try to apply it to an assembly. Because when we're measuring the height of this individual part, we're not taking into account these low spots. We only talk about the high spots, the three high points that contact the gauge surface. Unfortunately, the assembly cares about those low points, because you may have a mating part that interacts with it in an unexpected way. So I think the standard, or the most common way people would go about doing a stack up like this to figure out the math, is that they would say, okay, well, the nominal on my parts is 10 millimeters, and I've got a profile height of 0.02, so converting that into plus minus, I would say, well, this is 10 plus minus 0.01, and then it's the same for this one, it's 10 plus minus 0.01. And then doing some addition, some simple addition, we'd say, okay, well, the overall height is 20 plus minus 0.02. Following this math, we could say that we've got a max overall height of 20.02 and a min overall height of 19.98. But this is not quite complete. Let's say we put a note on the two blocks saying, this side's Datum A. They need to be facing each other. What we need to do, the max is correct, but what we need to do is we need to take the minimum and then include the datum overlap. So in this case, the datum overlap is pretty simple because the parts are the same. we have to say basically the minimum from this plus minus the overlapping flatness, which is as much as 1 millimeter. So minus 1. So the new minimum, or the correct minimum, is actually 18.98. So I can imagine the question people are thinking, well, what if I put a note on this block and I say, don't stack the datum A's together, keep that, keep those surfaces apart. What if I do this scenario where I do the profiles together, or what if I do the datum A and the profile in contact with each other? Is there overlap? Is there datum overlap? There, I've got a datum, but it's not touching another datum. And the answer to this question is fortunately no. And okay, well, why is that? Let's really read through what this is saying. So this is saying we place this block down on a simulated datum with the flatness side down on the simulated datum, and then 10 millimeters up, this top surface can vary within a profile of 0.02. So there is a boundary on either side, 0.01 millimeters of this nominal profile that this surface can vary within. And we've already taken that into account over here with the plus minus. So there would be nowhere for this datum A to violate that surface or to overlap with that surface. There's a hard boundary. So if this surface is at the minimum material, we don't measure a surface profile from the top unless it's a tangent plane. But this surface cannot do this, which is the only way we'd be able to get something like datum overlap, or surface overlap, I guess it would be called in this scenario. Now, what is the mathematical rule? So let's say we've got two parts, part 1 and part 2. Part 1 has an overall height measured from its datum surface of a plus minus x, and the datum surface has an allowable variation of m. And then part 2 has a measured height from its datum surface of b plus minus y, an allowable surface variation of n. So if we have those two surfaces, those two datum surfaces overlapping, we can have a maximum height of the nominals of the two, a, which is the nominal of part 1, plus b, which is the nominal of part 2, plus the sum of the two tolerances. So that's our maximum allowable assembly height. But the minimum allowable assembly height is the nominals, the sum of the nominals, a plus b, minus the tolerances, minus the lesser of the surface variations n and m. So if part 1 has an allowable surface variation of 1, and part 2 has an allowable surface variation, so around the datum face, of 2, well, you only subtract 1. I'm going to try and drive this point home with one final example. Let's say we had them make a second gauge block, but this time the flatness of the datum A is 0.5 millimeters. So they produce the part, and again, they basically nail the overall height. Exactly 10 millimeters, and they decide to use up the entire allowable surface variation on the datum A. In the assembly, that ends up looking like this. So we have the datums penetrating into each other, but we only have them overlapping by the lesser of the two allowable surface variations, which is 0.5, which in this case means that we have an overall height of the assembly of 19.5 millimeters. Does this make sense based off of the math that we went over in one of the earlier slides? Well, we've got a maximum height of the assembly of 20.02, and this doesn't change. And then we've got our minimum of 19.98, and then we include the lesser of the two surface variations. So in this case, 0.5. So we subtract 0.5, which gives us 19.48 as our minimum height. Hopefully your answer to this question after watching this video is yes, you should be taking this into account. I think there's a little bit of nuance there because if you're making parts with micron tolerances and your assemblies sort of only matter on the millimeter tolerances, maybe it's not so important. But for the most part, if someone's got a micron tolerance part, the assembly likely matters on a micron tolerance, in which case this could make the difference between an assembly working and not working. Anyways, hopefully this was helpful. Have a good one.